Am I audible? Anyone? Can you please let me know whether I'm audible? Okay, yeah, yeah. So we will just start within another 1 or 2 minutes. Like, let us wait for others to come, and after that we can start. Like probably by 5:03 or 5:04. Yeah. So yeah, I guess we can start. So let. Am I audible? Again, I just want to check once. Hello. Anyone? Can please let me know whether I'm audible? Yeah. Okay. Okay. Thank you. Thank you so much. So let me introduce about myself first before we start the today's live interaction class. So first of all I welcome you all to the second week live interaction course for the course on renewable energy engineering, solar, wind, and biomass energy system. I am Pratyumnan. So I am a PhD scholar at the Indian Institute of Technology, which is offering this same course. So yeah, let me share my screen and then we can proceed. So is my screen visible? Yeah, okay. So this is the second live interaction class for the Renewable Energy Engineering Solar, Wind and Biomass Energy Systems course. This is given by the course instructors Professor Vaibhav Visham Gaur sir and Professor Ananda Lakshmi ma'am from the Department of Chemical Engineering, IIT Guwahati. I am the host for today's live interaction course. So I am the teaching assistant. So I am Pratyumnan. I am currently pursuing my PhD in at IIT Guwahati as well. So yes, so last week was pretty intensive with regards to calculation. We got to know about many different kinds of solar angles. We got a brief introduction about the renewable energy, how what about the time scale for the how renewable energy is comparatively a better option for us in the future compared to the other fossil fuel, which will take 100 to 200 years for preparation, and how we are actually losing out the fossil fuels, and some of the estimates about how much about by what particular time we will completely lose them. So and why we should actually shift or focus more towards the renewable energy concept, and then we moved on saying on focusing on the specific topic of our course, the solar, and how and what are the direct way of harnessing the solar energy, indirect way of harnessing the solar energy, how the solar energy is an indirect source for both the biomass as well as the wind energy system, and how biomass is also a cleaner and a green energy source. I believe that one of the attendees have actually asked that question, and it was an interesting question and a good question as well, because biomass as such, if you see, we burn them and it pollutes the environment, but still we call it as a green source of energy, because the amount of carbon dioxide that was taken up by the plant is released when they die and then they are burned. The amount of energy when the biomass is burnt is extracted, but the carbon dioxide that was used up by the plant is again goes back to the atmosphere. So the carbon neutrality is maintained within the environment. And then we moved on to see about different types of solar angles, like declination angle, slope, hour angle, surface azimuthal angle, and then we calculated the monthly average daily global radiation, hourly global radiation, lot of formulas and lot of calculations, and it was all very tedious calculations with complex formulas which has to be properly went through. So this is kind of a workflow sheet. So since the process is very tedious and is quite long, and it could easily take more than an hours of time, so you need to have exactly what to do in order to proceed properly in a correct direction. So I have created a workflow sheet for any kind of question that at the end it comes out to say stating that calculate the solar radiation falling on the surface. You could use this as your kind of a guide to go through and solve your problem. So first is you have the slope of your tilted surface, which will be given in the question obviously. Then you need to know the latitude of the location. So how to convert, so how to identify the latitude of the location, and then how to convert the location which is given in terms of degrees, minutes and seconds into completely degree for our calculation purpose, like taking the minutes part and then dividing it by 60 and then adding it to the angle will give you the total angle. Then the declination angle, which we calculated using the nth value, nth day of that particular year. Let's say for example January 31st, so the value of n will be 31. In case of our example was August 16, so the value was around 228. And then we calculated the hour angle by using the solar time that we were given. So our in the previous example that we did it in week 1, our solar time was 16 hours, so that is 4 p.m. in the evening. So we got our hour angle to be plus 60 degrees, 60 degrees. And then by using sine convention, since this hour angle is towards the afternoon, since the 16-hour solar time we have taken for our purpose of calculation is in the afternoon, so we used minus 60 degrees. and then the surface azimuthal angle. So what kind of orientation does the surface have? And then we calculated the hour angle at the sunrise and the sunset, and we took an assumption at the sunrise and the sunset that the sun rays fall parallel to the surface. So we took the value of theta as 90, and then we proceeded on to calculate the omega s and omega st. Then we calculated the duration of the sunshine hours, the s max. So td is equal to, the formula is td equals to 2 by 15 times omega s. So the hour angle at the sunset, at the sunrise. Then we calculated the monthly average daily global radiation Hg bar using HO naught and S max. Then we went on to talk about hourly global radiation Ig bar using Fc, which is the tilt factor, I naught, Hg bar, which we calculated from the previous step, and HO. Then we calculated the radiation coefficients, Rb, that is the conversion factor for beam radiation, Rd, conversion factor for diffusive radiation, and Rr, conversion factor for reflected radiation, using the value of beta and rho. Rho is basically the reflective coefficient. Its value was 0.2 in case of normal ground, ordinary ground, and 0.6 in terms of the snow covered ground. So and then at the end we calculated the solar radiation falling on the surface, IT, using IB, that is the beam and the diffusive radiation. So the beam radiation is the one which actually falls directly onto the surface, the sun rays that falls directly onto the surface without undergoing any kind of scattering by the atmosphere is the beam radiation, whereas the ID is basically the diffusive radiation which undergoes scattering because when the sun travels, it also travels through the atmosphere. So because of which diffusion of some of the sun rays actually undergo diffusion. So that diffusive component is ID. So these A, B, C, D, E is basically important for the calculation of angle of incidence and zenith angle. And then all the other parameters A, B, C, D, E, F, G, these all together are important for the calculation of the other parameters which is used for calculating the global radiation, the intensity percentages, intensity of the solar radiation that falls on the surface. So this is the workflow sheet. So I hope that if we use the same way of solving, we will be comfortably and conveniently we can calculate the value of IT. So I hope everybody remembers about how we solved the problem in the week 1. Over there I will tell you the difference. Over there we consider the value of beta to be 45. Here we consider the plate to be on the horizontal ground. So your solar collector, the flat plate collector, instead of having an angle theta, it is on the ground. So now we have to calculate according to this steps. We have to calculate the declination, hour, and then monthly average global radiation, daily average monthly average daily global radiation, monthly average hourly global radiation, and then the total solar radiation that is falling onto the surface. So since we have already done that, and I hope that the attendees would be able to now comfortably solve, so I will just give you a moment or so to actually think about how much amount of effort do we require compared to the previous problem, because we have calculated a majority of the parameters during the last week's course itself. For example, let me just move on to that particular. So yeah, so this was what we did in the previous lecture. So where we considered an angle of 45 degrees from the ground. The flat plate collector is at an angle 45 degrees. So we calculated everything, almost declination angle, hour angle, everything. So here also we have to calculate the same thing, but we just need to change a few parameters, because the beta value is the only one that is changing. We have 0 degrees, but it's not necessary that all the parameters that are actually given here has that value is a function of that beta. So there are many places which is not a function of beta. So I hope everybody would be comfortably able to solve now. So I'll just give a moment of like 1 minute or so to for you to think about what are the parameters will actually change when we change the value of beta. So here we are assuming beta to be 0 degrees. So I just want to know what are the parameters that will change, and what are the parameters that will remain constant, and how we progress towards working this kind of a problem. This is almost a similar problem, so I'm expecting responses from the attendees audience here. Anyone? So our angle of incidence is a, as you know, the formula for the angle of incidence is this: cos theta equals to sine phi sine delta cos beta and cos beta cos gamma cos omega sine beta plus cos delta cos phi cos delta cos omega cos beta minus sine delta sine beta cos gamma plus cos delta sine gamma sine omega sine beta. So here, since our flat plate is at the on the ground surface, beta will be 0. So cos beta will be 1 plus cos beta plus here the sine beta will become 0 because sine of 0 is 0. Cos beta will be 1, sine beta will be 0. So the formula will reduce to sine phi sine delta plus cos phi cos delta cos omega. So if you see this equation, this is the same as what we did for the previous example, the zenith angle. So when your beta becomes 0, that means your normal to the surface and then your sun's radiation. So your normal to the surface will be like this, and then the sun's radiation will be this. So we know that the definition for the zenith angle is the normal to the horizontal surface, the angle formed between the sun's beam radiation and the normal to the horizontal surface. So here also the case is same. Since the flat plate collector is at the ground surface, the normal will be uh, so it will this will be the surface, so normal to this will be in this direction. So this is same as that of the zenith angle. So if you substitute the values like, so if you substitute the value as of 5 as 23 sorry 20 from the previous example. So if you substitute the value of phi as 28.64 and delta, that is your declination angle, which we calculated in the last week, as 13.54, and your omega, that is the hour angle, minus 60 degrees Celsius, then you will be able to find the value of theta. So let me just show that. So yeah, here, so our declination angle is 13.45, our angle is minus 60 degrees Celsius, and our latitude of the location is 28.64, because we have taken New Delhi. So New Delhi is at a latitude of 28.64 degree north. So if you substitute all those values, you will get the value of cos phi, cos theta or cos theta z, both are same, as 0.5388, and if you take the cos inverse, then you will get 57.433 degrees. So this is your angle of incidence. So since this angle of incidence is a function of beta, so if I hope everybody remember, the last lecture, last live interaction, we told that the theta is a function of phi, that is your latitude, delta, that is your declination angle, beta, that is your slope, and then your gamma, which is basically the orientation of the flat plate collector, and omega, which is your hour angle. So here beta is a function, so that is the reason your value of cos theta changes. Over there the value of cos theta was around cos theta was 0.478, that is 61.41 degrees, but here the value has changed. That is because beta theta is a function of beta also. But apart from that, if you see all the other parameters like omega, omega st, s max, hg bar, hd bar, ig bar, id bar, and then even the value of ibn, id, ig, and ib, that is your diffusive radiation, global radiation, beam radiation, and then your the normal beam radiation, that is the radiation of the sun normal to the surface. All these values do not change because they are not a function of beta. So the calculation becomes much easier here. These all values actually remain the same. So here what will change is your angle of incidence, and then if you remember the solar radiation that we spoke about, the solar radiation falling on the tilted surface can be expressed as a function of RdId plus RbIb plus Rr of Ib plus Id. Rd is your, as I said, conversion factor for diffusive radiation, conversion factor for beam radiation. Rr is your conversion factor for reflective radiation. So Rb and Rd values are, let me write here. So Rb Rd equal to 1 plus cos of beta, that is cos 0, divided by 2. So cos 0 is 1 and this thing will be 1. And your Rr is rho into 1 minus cos beta divided by 2, which is rho. Here since we have taken the example of New Delhi, here we took the example of New Delhi. So in New Delhi there will not be any snow covering the ground surface, so the value of rho will be 0.2, that is the reflective radiation coefficient will be 0.2. 1 minus cos of 0 divided by 2, which is 0.1. Oh sorry, 1 minus cos 0 will be, it will be 0. So your value of Rd, Rr is no. Rb is cos theta I by cos theta z. So here theta I is nothing but is your incident angle of incidence. So that value is around 0.5388, and the cos theta z is the same. So theta I and theta z here is the same. So the value will be 1. So Rd you know is 1. We calculated as 1 plus cos 1 plus cos beta by 2. So that is 1 plus cos of 0 is 1, that divided by 2 will be 1. So we got the value of Rd. Rr is 0, Rd is 1, Rb since theta and theta z are same is equal to 1. So It will be RdId plus RbIb. So which is your value of Ib is 1476.38, your value of Id is 334.668. So the total value of It is 1811.05 kilojoule per meter square hour. So likewise similarly you can do for at 90 degrees. So if you do at 90 degrees, similar steps. Here your value of angle of incidence will change because here beta will become 90. So cos of 90 is 0. So your theta and theta z will no longer be the same. So rb value will change, and rd, so 1 plus cos of 90, cos 90 is 0, so rd will be 0.5, rr will be 0.2 into 0.5, that is 0.1. So your RD, RR and RB values will change, and RB value will be around 0.34. So your IT, if you calculate, the value will be around 1282.98 kilojoule per meter square hour. So this I just showed it as an example of how does your IT value, that is the solar radiation falling on the tilted surface, varies as a function of the tilt of the surface. So how do you vary your, how does the total the instantaneous value of the solar radiation falling on the tilted surface vary as a function of theta. But it's not only about theta, there are so many other factors also that contribute. So you can always do it for varieties of theta and plot a function, or probably different months. How does the value of IT varies as a function of months? Because here we took August 16th as an example, but how does it vary for every single month? So that you can calculate and then you can plot it, or you can study about the variation of the value of IT with the time. Here we took the our solar time as 4 p.m. 16 hours, but how does it vary across the day of the sunshine that is available? How does the amount of radiation varies? So you can do a lot of different examples based on this itself. These two examples that I gave last week and this week what we are doing are just for showing how to proceed with the steps, because since the calculations are very tedious, as I always been saying, so we need to practice many problems so that we get a good grasp on how to solve these kind of problems, because these will lay the foundation for our week 2 class, where we will discuss about how to design the flat plate collectors based on the amount of intensity of the radiation that falls on the flat plate collector. So we need to have a thorough understanding on how to calculate IB, ID, IG, IT and various other parameters, so that we can conveniently sail through that particular part of the uh, calculations, or the design part we can easily go through. So this will vary as a function of many different parameters, and it is of your interest. You can always vary multiple parameters, use Excel and then vary lot of parameters and then plot a graph to check how does the solar radiation varies as a function of beta, then the day, the month of the year, the days in a particular month, the time in that particular uh, day, the orientation. Here we assume the value of gamma is 0 because it was pointing towards the south, but if it points towards a different angle, how does the global and the other kind of beam radiation varies as a function of that? So a lot of different parameters can be varied to check and optimize at what particular time we can get the most maximum and optimize the amount of radiation that we want. So if anybody has any doubt up till here, then please let me know. Yes, anybody? Okay, then I will actually progress to the next question, because that's a quite an interesting question. Here these two are just for solving purpose, to get a good this thing on our mathematical skills. So the question number 3 is quite interesting. So I request everyone not to see how we have solved, but to first read the question and understand and think about how to go for it. So I'll just read the question. At a certain location of particular latitude and longitude, an unshaded pyranometer and a pyrheliometer is placed, which records 695 and 721 watt per meter square respectively on September 15th at 10 hours. A flat plate is installed at an angle of 13 degrees and oriented east of south at 35 degrees. Calculate the flux incident on the collector. So here previously we have assumed that the value of gamma, that is the orientation of the flat plate collector, is 0 because it was pointing towards the south. Here it is pointing east of south at an angle of 30 degrees. So now we are supposed to calculate the flux incident, and in order to calculate that, they have also given one more thing as pyranometer, pyrheliometers record as 695 and 721 watt per meter square. So here the thing, pyrheliometer, if you had observed carefully in the lecture, in the week 1 lecture, I guess the very first video, it was clearly described about the working principle of pyrhelio and pyranometer. So your pyrheliometer reads the beam normal flux, IBN. So the sunlight that falls onto the beam normal, and then your pyranometer reads the global radiation, that is both your beam as well as the diffusive radiation, whatever the radiation that is comes out from the sun rays to the atmosphere, both including beam plus the diffusive. So this is the concept here. You should have an understanding on what the pyrheliometer can read and what the pyranometer can read. Your pyranometer can read the global radiation that is falling onto the tilted surface, which is a combination of both the beam and the diffusive, that is the entire radiation that is coming from the sun, and your pyrheliometer reads the beam normal flux to the tilted surface. So here again we have to calculate the parameters, that is your latitude of location, phi value, which is 25 degrees and 47 minutes, that is comes around 25.7833 degrees. So we divide 47 by 60 and then add it to 25 degrees Celsius. Let me show it once. So it's 47 minutes, right? 47 divided by 60 . 47 divided by 60, oh no, sorry, 47 divided by 60, 0.7833 plus 25, 25.7833 degrees. And your slope is given as 13 degrees, so because it is written a flat plate is installed at an angle, and your omega value, that is your hour angle, is 10 minus 12 because it is given 10 hours. So the formula is solar time minus 12 into 15 degrees, and I explained even in the last class we discussed this. 15 degrees is because the earth rotates for 360 degrees in 24 hours. So 360 divided by 24 will be 15. So 10 minus 12 is minus 2 into 15, minus 30 degrees, but your 10 hours is in the morning. According to the sign convention, if your solar time comes in the morning, it is assumed to be positive. So your omega value will be plus 30. And then again, delta is your declination angle. The value of n is 258 because September 15th. So assuming it's not a leap year, so September 15th the value of n will be 258 and the calculated value of delta will be 2.216 degrees. So let me just show that also. So September 15th, January has 31, 28, 31, April is 30, May is again 31, June is 30, July is 31, August is 31 plus 15, 250, that is September 15th, and then your angle of declination angle. So 284 plus 258. So I hope everybody is also noting down this all in their notebook, because as you keep practice, it will be like beneficial for you to solve other kind of problems that comes in the assignment, or if a similar kind of problem comes elsewhere, because without solving this might be quite difficult. Into 360 divided by 365, so 534.57. So sine value of that, sine of 534.37, and its sine value is 0.0981, that into 23.45, 2.3, 2.21, almost the same. So this is the value of delta, that is your declination angle, and then we move on towards finding your zenith angle, that is sin phi sin delta plus cos phi cos delta and cos omega. Your delta is 25.87. I'll just zoom this in. So your phi value is 25.7833, your delta is 2.216, your cos delta and your hour angle is plus 30 degrees. So if you calculate cos phi z, that value will be 0.796. So since the pyrheliometer reads your beam normal flux, so the 721 that is given here is your IBN, and your pyranometer reads your global radiation, as we know from its concept. So that value will be 695 watt per meter square. So this is the relation, IBN is equal to IB by cos phi z. So this is the beam normal, this is the beam flux, and beam flux will be beam normal flux times cos of phi z. So what is normal to the surface, if you take the component of that, you will be able to get how much amount of the beam radiation that is falling on the surface of your flat plate collector. So IB will be 721 into 0.796, which was calculated. So the value will be 721 into 0.796, 573.916 watt per meter square. Your IG is global radiation, that will be a sum of your beam radiation plus diffusive radiation. So beam radiation, so you can calculate the value of diffusive radiation as global radiation minus beam radiation. Global radiation is 695 and beam radiation you got as 573.916. so if you subtract both, you will get 121.08. 121.08 watt per meter square. So I hope after this people will be able to solve, because this is again the same way I did it in the previous example. The calculation after this, what follows is your calculation of RD, RB and R, and then your the final IT calculation. So this will be the flux that is incident onto your the flat plate collector. So I hope now everybody will be able to solve. So I am not going to show the answer right now. So I'll just give 2 minutes time and then let's begin after that, because that particular calculation is, this is very important, because from here on, from these four, okay. Yes, Rohit, I guess you have raised your hand. Rohit, okay, I guess that was just because some other kind of disturbance. Am I audible to everybody? Anyone? Yeah, okay. So I'm okay. I guess some other kind of disturbances was there. So yeah, these four or five these four value calculation is important. So I'll just give you a minute and then I'll see how many written back with an answer. So anybody has any doubts like on any calculation of any particular value or somewhere in the concept part any doubt is there, so they can you know uh, unmute their mic and tell me, or you can also post on the chat box. So I hope everybody would have solved and they do not have a question. So I'll be just now saying how to like you know telling it again for this particular problem of how to solve the how to get the value of IT. So RD, as we have seen previously, is 1 plus cos beta by 2. So our beta value that is 13 degrees. So 1 plus cos 13 by 2 was 0.987, and our RR value is zero point 0.2 as rho because it's for ordinary ground. 1 minus cos 13 degrees by 2 is 0.002. RB is your cos theta I by cos theta Z. Cos theta I you can calculate because that's the reason I have not given specifically, because uh, it is for the audience and attendees to calculate that value, and it would be around 0.774. So if the value of RB will be 0.972. So IT, as you know, is IBRB plus IDRD plus RR of IB plus ID. So that is 0.97 into 573.916 plus 0.987 into 121.08 plus 0.002 into 695. So your value of IT will be around 677.594. Let me just show that. So 0.972 into 573.916 plus 0.002 into 695 plus 0.987 into 121.08, 678.74. Just a little bit of probably that accuracy but anyway it's almost the same. So this is the value of IT. So here it concludes for this week 1 lecture. So here this is only for week 1. So as a recap for week 1, if we say, we have learnt about how to calculate the solar angles, and then 3 different problems, how the pyranometer and pyrheliometer can is used for measuring 2 different kinds of radiation, and how we can use those to calculate what we want, because that IB and Ig value will not be given straightforward in the question. It will be given in terms of this. This is the way to trick, because you need to know actually what each one will record, so that you can actually solve the problem. So that one we have seen. So I guess 3 problems would be enough, and at the end of the lecture I will also tell where you can look for more problems, because practice will make, for everybody to become more efficient in knowing how to progress with the question, as well as in these calculation errors. It will help us eliminate calculation errors. So I hope nobody has any doubts with respect to the 3 questions that we solved. The question number 1, in case if anybody is new, they are attending it for the first time, the question number 1 is given already in the NPTEL portal for this particular course, the course portal, in the problem solving session for Jan 2024. If you go, you can see both the recording, also the particular PowerPoint presentation. So from there you can actually get to know how we solved that particular question, and use that and can solve the other questions or other model questions or practice questions for your practice purpose. And yeah, so here it concludes the week 1. So now we move on to the week 2. So here we will be discussing, so the week 2 course is particularly focused on non-concentrating solars. So the week 4, if when we go down the line, we will be talking more about the concentrating solars. So here for the week 2 course, if you see, all the 3 lectures, 3 videos have been specifically made sure in such a way that it focuses on non-concentrating solar collectors. They have been dedicated for the non-concentrating solar collectors. So yeah, 1 minute. So this is the working principle of a flat plate collector. This is a flat plate collector. So here you have a thermal insulation, the fluid tubes, you have a black absorber plate, and you have a transparent screen, and then the solar radiation hits your surface, and then the energy can be stored. So it's a very simple process. So here the main principal mechanism that is governing the flat plate collector is that the heat transfer between the radiant energy, that is the incident sunlight, is equal to the sensible heat of the working fluid. So this particular heat energy will only be taken up by the working fluid. So the useful heat gain, here we describe a concept of useful heat gain, that is equal to QU, is what is basically taken up by the fluid. So this QU will play a very important role in our further calculations as we go through this course. So here it is so if you see the flat plate collector, it consists of a transparent screen. So these transparent screens have a particular role. So here what they do is that 1 minute. The flat plate, the transparent screen allows the solar radiation to fall onto the surface. It absorbs the solar radiation, which then moves to the black absorber plate, but it also prevents the radiations from coming out, the long wavelength radiations from coming out of this particular system. So transparent screens play a very important role, because they allow the solar radiation, but at the same time they also minimize the re-radiation losses that can happen. and then we use a black absorber plate. The reason why we use black absorber plate is basically because to increase the amount of energy capture. The black as such has the ability to absorb all the radiation, and it will not allow any other it will not allow the wavelengths to reflect back. So because of which, it since it absorbs all the light, so it has the better ability to capture the heat. And then you have the fluid tubes. So here the fluid flows, so the heat that comes to the black absorber plate is transferred through the heat transfer process of conduction and convection. It gets transferred through this fluid tubes. The fluid in the tubes gets heated up, and then the heated fluid goes into the other kind of storage units, which then can be used for a number of varieties of application. And then here you use a thermal insulation, which helps in making sure that whatever amount of heat that is absorbed by the flat plate collector does not get lost. It will help in minimizing the losses due to convection and the radiation as such. So here are the design considerations. So I'll just ask a basic question. So in case of any engineering model, or if you want to, in case of any engineering model as such, what should be our, what do you guys think should be our primary goal be? So if you take any engineering model, or if you take any model, we always want to maximize something. So what is that, what is that we always want to do? If we take a process as an engineer, what always comes to our mind? Can anybody tell? Yes, model making is one, but I am looking for an answer uh, like if you have a process, what do you and if they ask you to actually modify something, or what would you actually do to that process? Like what would be the thing that you would like to modify? Like what should be your end goal of that particular modification or the making of that model? It should be to increase the efficiency. So as engineers, we are always interested in making efficient process. So we always want to improve the efficiency of any process at the at a very cheaper or low cost rate. So we always, irrespective of what the process is, not just about the solar collectors or the flat plate collectors that we are discussing here, any process that we take, let's say for example the electronic gadget, we always want to develop a process in such a way that we can make them small, and then we can try to use them for a very long time efficiently. Any kind of model that we take, we always look for one thing, is to reduce the cost of it and then maximize the efficiency of it. So that's what again we are going to see here, and that is what is our design consideration here. So the design consideration that we want to keep in focus while designing is maximizing the solar absorption. Yes, and that is one of the reason why we use a black absorber plate. It's called as a selective surface. So the black absorber plate absorbs all the radiation, so it will be able to heat up the object. In case of a white plate, in case of, if you take a white plate, it will almost reflect all the wavelengths of the light, so that may not get heated up as fast as a black object, and then increase the useful heat gain and minimize the losses. So that is a part of your thermal insulation. So you always want to make sure that the model that you use has negligible amount of that particular parameters getting lost. Here it is the heat. You don't want to lose the heat to the environment, and you want to improve the amount of useful heat that you will get. Apart from losing into the environment, there will be also a lot of other losses that will be involved in a particular process. So how we can minimize those losses and increase our useful amount of heat, so that we can increase the efficiency of our process. So these are the design consideration. You need to maximize the solar absorption. So usually for that, as such, we have seen examples. We usually tilt our surface or orient our surface in such a way that maximum amount of solar radiation can be absorbed, or probably try to harness more amount of that radiation at that particular time. So so that is the reason why I encourage everybody at the initial to actually to actually work out more on this, as more on finding the value of IT as a function of month, day, time, theta, and then your phi, the orientation, so that you can actually observe at what will be the maximum amount of solar radiation that you can absorb. And then and then about your minimizing heat losses, which we will see now. So the QU is there taken up by the fluid. So these are the design equations. So your QU. So here, for the time being, this week we will be discussing on these equations, because these are again very complex equations like we saw in the first lecture, and you need to have an understanding about what does these parameters are, because this will be helpful while solving the problems next week. So your QU value, QU, that is your useful heat gain, is equal to AP. AP is nothing but it's your area of the plate, and UL is your heat loss coefficient. So as I said, you cannot minimize all kind of losses. You can minimize the loss of heat to your environment, but still, as such, in an inbuilt system or an inherent system, you will be left out with a lot of other losses that will come up. So you have to account for that. So this is UL. TPM, this is basically the mean temperature, the plate mean temperature. So you have a plate, but you do not, it is not always necessary in a real condition, in a real time condition, all the points in that particular plate are heated up at the same temperature, at the same rate and the same temperature. One point might be at a different temperature compared to the other, because of the lesser amount of radiation falling on the surface, or probably due to the tilt, the way the flat plate collector has been constructed, and many different reasons. So your flat plate, that plate where the solar radiation fall, may not be in the same temperature, it may be at the difference. So we need to calculate the mean temperature, and your TA is your ambient temperature of that particular surroundings at that point of time, and FR is your heat removal factor. So how do you calculate the value of S? S is your solar flux, is a function of IT times tau alpha average. So this can be expressed as IBRB tau alpha B plus IDRD plus IB plus ID total times RR of tau alpha D. So this tau alpha D is due to diffusive radiation, and tau alpha B is due to beam radiation. Sorry. Yes. Oh, just are you able to see now? Okay. Sorry, it's my mistake actually. I didn't put in the full screen mode. So, let me just I'll just say those things again. So these are the design equations. So based on these equations only, you will be calculating your the QU and then the efficiency of your flat plate collector. So AP is your area of the plate, that is the flat plate collector, that particular cross sectional area, which you can say effective cross sectional area where the solar radiation actually falls. S is your solar flux minus UL. UL is your heat loss coefficient, because as I said, all the heat loss cannot be minimized or can be reduced. So there will be heat losses that is happening inherently within the system due to multiple factors, like the the flat plate, the absorber plate, and then your tubes, if they are not at the same temperature, there will be a loss of heat. So that is one particular thing. And then when the water, when the heated water actually moves to the storage unit, due to its motion, some amount of the heat loss might happen. So all these things has to be considered. So there will be a heat loss coefficient UL. TPM is your plate mean temperature, because as I said, all the plates need not be heated up equally, and at the different points temperature will be different. So TPM is that. TA is your ambient temperature, the surrounding temperature at that particular time, day, and Fr is your heat removal factor. So S can be expressed as a function of IT tau alpha average, which can also be expressed. This is tau alpha average. This is a simplified equation, and you can use this, but a more exact way of calculating is this one: IBRB tau alpha B plus IDRD plus IB plus IDRR tau alpha D. This tau alpha D is due to diffusive radiation, and this is due to beam radiation. Now you can also, this is the exact way, but if you do not want to use the exact way, then another one kind of assumption is that you can use this S value S as 0.96 times of tau alpha B, that is due to beam radiation. I'll just write this here. This is all, actually it is mentioned in the lecture, but I am actually repeating so that everybody will be able to be confident on what are the different terminologies. Times tau alpha, I just write Ta times beam radiation. So 0.96 times of your tau alpha B can be taken as the value of x. This is a very approximate measure, but if you want, you can also calculate using this equation. So if you remember, the reason why I said the value of over there, these 4 or 5, this calculation is very important, is because of this. You need to know the value of IB, RB, ID, RD, IB plus ID. You have to have a very good understanding of these values, so that you will be able to calculate here the value of S, and this S value will directly influence your QU. Your QU will directly influence your efficiency. So if there is any mistake here, then that will affect your S, which will affect your QU and indirectly the efficiency. So these parameters have to be very precisely calculated. And your IB plus ID is nothing but your IG, that is the global radiation. Here the heat removal factor calculation is also, this one is given. So these are the three equations, because your Fr has F dash, and the F dash has a phi as unknown, and you have to calculate all these things. So let us move on to the next slide. And your RB, small rb, small rd, and small rr are calculated using the same formulas here. Here let me just write the value of RB also. Your RB is equal to cos, I'll write cos of I. You can use cos of theta I, it's just the notation difference, and cos of Z, that is the zenith angle. So these are the formulas: RD, RR and RB. These are the formulas: 1 plus cos B by 2 and rho into 1 minus cos B by 2 cos I by cos Z. So that small r, and for this capital R you can use the same formulas. So yeah, here S is the solar, as I said, solar flux absorbed by the plate, and you need to calculate. So the exact way of calculation is tau alpha. Tau is the transmissivity. So when a light falls on the surface, three different kind of things happen. Like one is absorption by the surface. So some amount of the radiation will be absorbed. Some amount of the radiation will be reflected back, bounced back, and some will transmit through the surface. So that is how the entire incident radiation. So if you talk about the incident radiation, that will have the three components. One is transmission, absorption, and reflection. So like that you have the coefficient. So each one will have their own coefficient. So transmissivity, absorptivity, and reflectivity, which will be there here. So to calculate your value of tau alpha b, this is the equation: tau times alpha p by 1 minus of 1 minus alpha p into rho d. So here alpha p is your absorptivity of the plate, so that will be given, so you need not bother. So absorptivity of your plate is a kind of, what is it, depends upon the material of a plate, it's a materialistic property, so that value cannot be changed much. So alpha p will be fixed, but tau value we can calculate. Tau is nothing but tau alpha into tau r. So tau alpha is due to the uh, absorption, and this is due to reflection. So and rho d is tau alpha times 1 minus tau r. So this transmissivity itself will have two different this thing, tau transmissivity components due to reflection and refraction. So this is the Snell's law. So because we need to know the Snell's law, because we have to calculate the value of tau r and tau alpha. So Snell's law is this. So can anybody tell when the Snell's law is basically due to the refraction of the light. So when a light falls on the surface, the light gets reflected, some part of the light gets reflected, and some actually transmits or refracts. The light refracts through the medium when it basically moves to the other medium. But can anybody tell why does a light refracts when it moves from one medium to other medium? Like, why is the value actually changes? Because here the value of theta I and theta r most of the cases will not be the same. So can anybody tell why is that a light refracts when it moves from one medium to other? Sorry. No, like angle of incidence, like a light, I'm talking about the refraction. Angle of incidence is just the angle that the light makes with the surface, the normal, like from you take the surface normal to the surface, and then the angle of light that is falling, the angle between these, if you take this as a horizontal surface and normal as this angle, if you see, will be the angle of incidence. My question is, why does a light refracts when it actually moves, goes from one medium to the other? Yeah, actually it is due to the density difference. But what actually happens in that, it should, a more specific answer, it is due to density difference, that is true, but a more specific, why does the light refracts due to the density difference? Like, what is that parameter that changes it? Actually, when a light travels from one medium to other, the refractive index of that particular medium will change. So in case of a density difference, actually this is exactly right, the light will not travel at the same speed as it travels in case of vacuum. If you see, in vacuum the light travels at a speed of approximately 3 into 10 power 8 meter per second, but that is not the case with every different medium that it goes. So the due to the difference in the speed of the light traveling through the medium, which is actually due to the medium, due to the density difference in the medium, the light travels at a different speed in the next medium, and due to this property, the light refracts. So the refraction, in order to calculate the angle of refraction, we use the Snell's law. So that is Ni sin theta I is equal to Nr sin theta r, where Ni is the refractive index of the incident medium and Nr is the refractive index of the refracted medium. And so once you know the value of theta r and theta I, you can calculate the value of rho 1 and rho 2. Rho 1 and rho 2 are nothing but the are nothing but they are basically the reflective components. So you can even see in the lecture, these equations are also taken from there. So these two components are the polarization. These two are the components of polarization of the reflection. That is, rho 1 is sine square theta r minus theta I, divided by sine square of theta r plus theta I. Rho 2 is tan square theta r minus theta I, and divided by tan square of theta r plus theta I. So you will be knowing the value of n1, ni, incident medium, refraction index of the incident medium, theta I, the angle of incidence, then your medium of refraction, what is the refractive index, and your, so if you know theta I, you can calculate sine theta I, you know refractive index of medium 1 of the incident medium, you know refractive index of the refractive index of the refracted medium nr, and with that you can calculate sine theta r, and from sine theta r, if you take the inverse, you can calculate the theta r. So you know theta r, you know theta I, you can calculate these both reflective components. So once you know this, you can calculate the transmissivity, which has a component both reflection and refraction. So tau r1 is 1 minus rho 1 by 1 plus rho 1, tau r2 is 1 minus rho 2 by 1 plus rho 2. So if you take a average of this, that is tau r1 plus tau r2 divided by 2, this is tau r. So you just calculate both these values, substitute here, and then if you add both and divide by 2, then you will get the value of tau r. So now you know tau r. Tau alpha is basically given by this equation, e power minus k, that is delta divided by cos of theta r. So your k is your thermal conductivity, and yeah, k is your 1 minute. K is your thermal conductivity and delta is the thickness of the plate, and cos theta r, obviously you know this is basically your reflection, and then the value of the k, usually it will be between 4 to 20. So this is what is actually known as the Boyer's law, so which will be helpful for finding the transmissivity due to absorption, tau alpha. So you know tau alpha, you know tau r, you know tau, and then now you know rho d. So with this you can calculate tau alpha b. Similarly, you can calculate tau alpha d, which we will see in the, while solving the problem, we will see that. Now we come for the collector efficiency factor, FR, as we said here. It is basically also called as the amount of heat removal factor. So FR is nothing but m dot Cp divided by UL AP into 1 minus exponential of f dash UL AP by m dot Cp. So m dot is the mass of the fluid. To be specific, m dot is the mass flow rate. Change here. Mass flow rate of the fluid used. M dot is the mass flow rate of the fluid used, that is kg per second. The units will be in terms of kg per second. AP is the area of the plate, the effective area of the plate on which the solar radiation is incident. UL is your heat loss coefficient, as I said, why there is a heat loss coefficient. Cp is the specific heat capacity of the fluid, which will be known to you. Majority of the time we use water. So in case of water, the value of Cp will be 4.18 kilojoule per kg Kelvin. Sorry. In case of water, Cp will be 4.18 kilojoule per kg Kelvin. Or if you want to express it in terms of calorie, it will be like 1.98 kilocal per kg Kelvin, or 1.98. I hope yeah, this one only. So this is the expression. Now your f dash is unknown. So here you need, so here if your f dash is called as the oh wait, I have written both here. This is my mistake. Fr is your heat removal factor. Just write it once. and your F dash is your collector efficiency factor. How much amount of the incident light is your collector being able to collect, like use it, like take it up. So that is what is the collector efficiency. So that is given by the formula 1 by WUL into 1 by UL W minus D naught phi plus D naught plus delta A by Ka D naught plus 1 by pi di HF. So here W is your pitch of the tube. So this is a kind of a different term. Pitch is nothing but it's basically you have two tubes. The distance between the center of the tube is called as your pitch. So pitch is nothing but is basically the distance between the two centers of the tube, and d naught is the outer diameter of the tube, di is your inner diameter, hf is your heat transfer coefficient. So that will be fixed for a particular case, because you have your absorber plate and you have your tubes. So there will be a heat transfer. So in order for the heat to transfer from your absorber plate to the fluid, you do require a heat transfer. That is basically happens using conduction and convection. So in order to account for that, you use this heat transfer coefficient, and this delta A by Ka d naught actually represents for the adhesion resistance. Here again your value of phi is unknown. So the value of phi here is given by tan h m into W minus D naught by 2 divided by m times W minus D naught by 2, where m is your UL by Kp delta P whole to the power 0.5. So UL is your heat loss, Kp is your thermal conductivity of the plate, and delta P is your plate thickness, and D naught is the outer diameter of the tube. So and it's not always necessary that UL value will be exactly given to you as such. It can be expressed as a function of UU plus UB plus US. So this is the final equation. So you need to like kind of have a good grasp of what these are actually, so that you know it will be useful for you to while we solve the problems next weeks in the class. So all these terminologies and what kind of units are used. So usually everywhere it is everywhere unless or until specified we will be using SI units, but some there are some places where we have to use some other units, like if not in meters, in terms of millimeter, centimeter, simple elementary level conversions. So but you need to have a grasp of all these formulas. And yeah, so here f dash is known, phi values, and then your UL is this thing, and yeah, here your UL, that is the heat loss coefficient, can happen due to multiple reasons, due to your UU, UB as well as US. So UU is due to the upper the heat loss that basically happens from the upper surface. UB is that basically happens from the bottom of the surface. Even though you have a thermal insulation, there will be some amount of the heat loss, and US will be from the side. So you have to calculate all these values, and we do have expressions which we will discuss further. So sometimes what happens is the value of UL will not be given to us. So we assume the value of UL as particular quantity, and then we do all these calculations, and then at the end we will calculate the value of we will calculate the UL value once again, and then find the amount of mismatch that exists, and then using that whatever UL value we calculate using this equation, we will recalculate it and then check the amount of percentage difference that comes on what we have used for calculation and what is coming out here. And then I guess here it is, that's all. So this useful heat gain, the amount of heat that is basically taken up by your fluid, is a very important concept. So does anybody have any doubt till here? Some other expressions if you are not able to understand, or some other kind of difficulties, or probably you are unable to understand something in the lecture, so you can ask me now. Anybody? So please let me know, because these equations are very important, because this is kind of the design equations. Actually, if we do not have a good understanding of this, then probably we might not be able to solve the other things. So that is the reason why I am specifically, you know, uh, keeping it here for some time, so that if anybody has any questions related to this, then please let me know now. So I'll just come back very soon. Please do not go. The meeting has not ended. I'll just come back very soon. I just have to take some water, and then I'll just return back very soon. Please be on the line. I guess we can then move on. Okay. So here we have come to know how to calculate, but how do we calculate the efficiency of the process? So I guess this would be very kind of like simple. So I hope everybody will be able to do, but I just want to know, because you know how you have done this here. So can anybody tell me now what will be the efficiency, how to calculate the efficiency, or what could be the formula for the efficiency? Anybody? Yes. Okay, so I'll just write it that here. Your QU will be, sorry, efficiency will be the amount of useful heat that you gain. So I'll just remove this, and then that is QU, the useful heat that is used, that can be used, divided by the total amount of heat falling on the plate. So now you know the efficiency, you know the expression for that. So can anybody at least now tell what could be the formula for that? See, it's easy because I have given the this thing, because and this is exactly what any efficiency equation will be used up for. So you just need to know now. Tell me what could be the the expression here, and I have given the hint also: useful heat, total amount of the heat that falls on the surface. So I expect somebody to at least tell. Okay, wait, okay, output by input, yes, then CS divided by RS. Can I guess the attendee's name is Gautam C. Can you just unmute and tell me, or like type it in chat box? What do you mean by CS by RS actually? Yeah, efficiency is as such is output by input. I mean, and that is what is probably I've written it in a statement: useful heat that can be used up, or probably that can be gained, divided by the total amount of the heat falling on the surface. But I just want you to actually think about what could be the expression that you will be having there. The expression will be, so express, so it will be eta, or for the time being I'm writing n here. I'll change this. Your useful heat, so that is probably the heat that you will be using up for your varieties of applications. So QU divided by the amount of heat that is falling onto your plate. So the solar flux S times, so it's a flux, so flux actually has a unit of watt per meter square. So that is not the heat, that is basically the solar flux. So that is not the intensity. So S is flux. So that has a unit watt per meter square. So you, and the QU is heat, that is the useful heat. So that will be in terms of watt. So watt. Yes. So you need to multiply this with AP, that is your area of the flat plate collector. So this is the efficiency of the step. Don't give capital Q, it should be small q, because it should be the heat transfer rate and not some yeah, QU. Okay. So this is the efficiency equation. Eta is equal to, or efficiency is equal to QU, that is the amount of useful heat that you can gain for varieties of storage application, divided by the S, that is the solar flux that is falling on the surface. AP is the area of your plate. Now these are some of the simple questions, but again you have actually kind of concepts to learn about this. So these questions I will not be answering. I mean, I will expect the attendees to answer first before me moving on. So you use a transparent glass cover, as I said here also previously. The glass cover that you use here is a transparent glass cover, and the sun radiation falls on the surface and then it moves to the absorber plate. Is or are used to minimize dash in a flat plate collector. So what is it? So please tell me what it could be. Yeah, it's QU, the efficiency. I see the chat box now. So QU, as I said, QU divided by SAP. So I hope people will tell the answer for the question number 1 here. Anybody? Because these are very simple questions, and I have actually told the answer also while describing the components of the system. Anybody? D. Are you sure you are answering it for the first question, or are you answering it for the second question? Okay, you mean to say that the transparent cover is used to minimize absorption of sunlight in a flat plate collector. So the thing is, here we are asking what is not, here we are asking not about the role, but about what we have to minimize. So the transparent flat glass cover is used for maximizing the absorption of sunlight. See, you want, as I said, the concept of efficiency, the concept of design consideration is that we need to maximize the stuff. So if we, so according to you, then it will become like we are minimizing the absorption of sunlight, so then we won't be able to get the proper what do you call, we won't be able to harness the total amount of sunlight that we have. So we are trying to minimize, so that will be kind of a detrimental to our, you know, the system. So Rajan has told optical concentration. Again, the question says is a transparent cover is or is used to minimize what? Optical concentration we cannot like if we minimize again the optical concentration, then the amount of sunlight that we are receiving will be less, so we won't be able to harness the energy. So we won't be able to, what do you call, so the amount of sunlight that will be we will be using it for our heating purpose will become less. So I guess I'm repeating the question. Here we are asked to minimize what? It's minimize. So conduction losses, yes, but again conduction loss, but that is not the primary motive of your transparent cover. So as we have eliminated all the options, so the reason why we use this to minimize the re-radiation losses. So as I told, a transparent cover is used that it will allow your solar radiation to go through the surface, but it will not allow the other kind of radiation, other kind of like reflected or re-radiated radiation from your absorber plate to the atmosphere. So it's like only incoming, outgoing will be very less. In this case, outgoing of the radiations will be very less. So here the answer is convection and the radiation losses. So the transparent glass cover here we are using is to minimize the convection and the re-radiation losses, because once the light falls on the absorber plate, some amount of the light will be, after that it gets heated up, it will, the some amount of the light will try to radiate back to the atmosphere. So the transparent glass cover should maintain it in such a way that it minimizes the what is called the radiation of the light back to the atmosphere. So the option answer is B. Answer is B. Now let's move on to the next question, and I have one more question, but I haven't typed it here, but I will be asking it as an open question. So question 2, in order to dash an anti-freezing solution, antifreeze chemical along with water is used. Work fluid in a solar collector during extreme winter season. So generally here let me generally discuss about the concept first. So here when we discuss the tube, I didn't discuss about this part. So water is specifically used for this purpose. The fluid that we use for transferring the heat is water. The reason why we use water is because it's, first of all, it's a universal solvent. I mean, that's a general term. And then the second one, the most scientific explanation is that it has a high volumetric heat capacity. That is, for a particular volume of the water that you have, the amount of heat that it can conduct is extremely very high. The amount of heat that it can conduct, or the amount of heat that it can store, is very high in case of that of the water. So for predominant applications we use water as the water for this heating applications. So water will be there in the tube, but unfortunately during extreme winter seasons, like let's say for example in Jammu and Kashmir, or probably in case of the other European or American in America, in the United States, there during the winter season the water will freeze. So once the water freezes, then the amount of the sun radiation that falls on the surface will not be able to I mean, they do get a pretty less sunlight during that point of time, but with that also we won't be able to actually melt that ice. So during that extreme winter condition, we are supposed to add an anti-freezing solution. So usually the anti-freezing solution that we use is ethylene glycol. So when you mix ethylene glycol with water, what happens is that it will help in making sure that your water does not freezes it. So with respect to that, I hope you can answer the question now. So the ethylene glycol will not allow the water to freeze even during that extreme winter conditions. So I guess people will be able to answer now. Here we talk about the transition of ice and water. So boiling point concept will come when you talk about water to vapor state. So here we are discussing about the water and ice, not water and vapor. So I guess option A is not the right answer. Yeah, it's decreasing the freezing point. So once you add the ethylene glycol, what happens is it will help in making sure that your freezing solution, your water does not get freeze. So by varying the concentration of the ethylene glycol that you have in the mixture, you can actually make sure that your water does not get freezed even at a very low temperature condition. Like, there are a lot of literature which actually discusses the percentage of ethylene glycol variation with with its melting, with its freezing point. So if you see, if you add ethylene glycol or glycerol also is one of the agent which can be used as an anti-freezing solution. So if you add ethylene glycol or glycerol in water at a particular optimized concentration, you can almost achieve minus 60 degrees Celsius freezing point of water. So that is a very extreme conditions which will be available only in a very certain locations in the world. So a minus 60 degree solution will not be able to make, will not be will can be helpful for us to prevent this problem of freezing of these solutions. So the concentration is approximately 40% ethylene glycol with I guess rest 60 percentage of water, but exact concentration is available in the literature. You can actually Google papers on varying the concentration of ethylene glycol and the anti-freezing temperature, uh, anti-freezing properties of ethylene glycol. Then you will be able to understand what should be the percentage of ethylene glycol that you have to add, so that your freezing point gets decreased to such a short extent. Because if you see minus 60 degrees Celsius, so usually water will not be able to freeze during that point of time. So the meager amount of sunlight that is collected during those extreme winter conditions can also be utilized for the varieties of applications. Because these kind of the water at that end, it will go to a storage tank, and from the storage tank it will be useful for varieties of heating application, like space heating, water heating, and solar air heaters, solar heaters, solar cookers. Like if you see in the lecture 3 specifically, we have discussed about a lot of different kinds of solar devices. First is the, I guess, solar heaters, then cookers also comes in between, so, and then solar water heaters, space heaters. There are many different applications of this. So here we just discuss about the temperature, what do you call, the heat gained by the liquid. So this heat gain will be useful for many other applications. And then the last question, which I haven't given here, but I'll ask it as an open discussion. So if you see the classification of these solar collectors, there are many different types of solar collectors. So what do you think will be this you know flat plate collector will come under? I have initially discussed there are two types of solar collectors in the classification. I didn't describe it, and I didn't write it down in the slide, but I have described it in words. So is anybody able to remember that? There are two classification of a solar water heat of a, sorry, of a solar collectors, and this is discussed even in the video also specifically. I'll give options. So one is basically your non-concentrating and another one is concentrating. So tell me whether our flat plate collector comes under which category. Is it your what do you call, non-concentrating or concentrating one? Yes, anybody? I mean, this is a very simple question. I have given the options also. So our flat plate collector is concentrating or non-concentrating one. Yeah, and sorry. So our flat plate collector is non-concentrating one. Here it's just a flat plate, and we do not have any kind of provisions for us to actually concentrate the solar lights. For example, if you go, I guess probably around the week 4 we will be discussing about the concentrating solar collectors, where we will be using parabolic or probably cylindrical curved structure, cylindrical curved structures for concentrating the uh, solar the sunlight. So in order to increase the efficiency, because as such flat plate, it falls on a flat plate, so you may not be able to get a lot of you may not be able to get that much amount of sunlight, whereas if you use a concentrated one, you will be able to harness much amount of the sunlight. And well, in case of real life application today, we may not have a rotating flat plate, rotating concentrating type collector, but as such as a prototype, there are also a lot of different models where you have a rotating uh, you know concentrated solar collectors. So as the sun, if you see, the sun rises in the east and sets in the west, so it has a complete motion, like it undergoes, it is at a different position at different parts of the day. At the mornings east, at the noon it's on top of our forehead, and towards the evening it actually sets in the west. So depending upon the direction, we can also, as a prototype, it is available that we can actually change the uh, the flat plate collector, change the direction of the concentrated solar collector to harness maximum amount of energy. So I guess yes, today we will be stopping here, because I have discussed everything that I want to discuss. So I'll be here in order to answer any questions, actually to know whether are there any doubts specifically. Actually, this week is a pretty theoretical week. We do not have many kind of problems to solve. But next 2 weeks will be very intense. We will have a lot of problem solving actually going on. Question number two, Gautam, you mean which question number two? Like, is it the numerical one, or is it the theoretical and decreasing the freezing point question? Yes. So what is like the doubt you have? Can you, in order to oppose the freezing, we can increase the boiling point of water. But as such, here we actually, as far as of I am concerned, if you um, if you increase the boiling point of water, but that will be probably the case where if you can actually use this in case, let's say, a place or a location, you take for example, which has approximately temperature of 120 degrees Celsius, which does not exist, because water boils at 100 degrees Celsius. So no person, or there can be no civilization at that particular temperature. But even if we take a hypothetical case where the temperature is, let's say, around 120 degrees Celsius, then in that case, if you try to increase the boiling point of water, let's say I take some particular component y, it can be any material, and then I can add it to the water, so that I can increase the, let's say, the boiling point to 150 degrees Celsius. Then in that case, even at that particular temperature, your water will not be able to boil. Even at 120 degrees Celsius, it will remain as a water. But here Our question is specifically, I will just let you know that question once again, is during the extreme winter condition. So so increasing the boiling point of water may not have an effect, because during winter season temperature decreases. So even if you increase the boiling point of water, let's say at 150 degrees Celsius, it may not be able to be useful for our purpose. So, but yes, suppose if you take a hypothetical situation as such I told about, where the temperature is around 100 and let's say yeah, 120 degrees Celsius, and then you don't want to your water to boil off, then probably you can add some agent and then increase the boiling point of water to 150 degrees Celsius. Then in that case water will remain as water even at that particular temperature. So yes, any other question? I hope you understood the this thing, or probably if you want to have more clarity, then I guess you can express it in, like, you can unmute yourself and let me know. So I hope you were able to understand the my answer to that particular question, because boiling here will not be useful, because in extreme winter condition we only talk about the case of water getting freezed. So yes, so if that is the case, then I guess okay, yeah, okay. So does anybody have anyone else have any other questions? So I just want everybody to actually work on those problems, and then work on those problems and then the formulas that was given, so that it will be helpful for the next 2 weeks, because next 2 weeks will be completely filled with problem solving. So I'll just write that here. Yes. Yeah. Actually, if you see, it was made available yesterday only. Yesterday, probably in the evening at 5 o'clock only the video came out. So if you go to the NPTEL portal, there the course portal, where you actually view the every week's video. If you see that at the end, you will have a problem solving session Jan 24. There will be a subsection. If you click on that, then you will be taken to the place where you have both the PowerPoint presentation of the last week, as well as the as well as the recording of this particular the week 1 session. It will be you will be directed to a YouTube channel. So from there you can actually watch the entire live interaction class for 2 hours. if anybody has no other doubts, then we will conclude the session. So let me stop presenting. So yeah, I would like to thank everyone who have come up to this session for today by spending their 2 hours of time from 5 to 7. The next week live interaction, that is the week 3 live interaction, will be on 11th of February, same time 5 to 7. So, and in case if you have any doubt, you are always welcome to give it in the ask a question tab in the NPTEL course portal. If you see at the header section, you can find one of the tabs. You can always post your questions there. So I would like to take this the rest amount of time as an opportunity for me to thank the NPTEL team, as well as Professor Vaibhav Vishant Gaud and Ananda Lakshmi ma'am, uh, for giving me this opportunity to interact with you all during this Sunday afternoon. And yeah, thank you so much for joining, and we will see next week. So yeah, bye.